Now we're going to take a look at planes in space. So we already talked about how to represent a line in space, but now we're going to talk about how to represent an entire plane in space. So if you consider the plane containing the point P, x1, y1, z1, having a non-zero normal vector n equals a, b, c, those are its components. Since the vectors are orthogonal that are given here, pn and pq, the dot product is 0. And this gives us that n dot pq equals 0. So ABC dot x minus x1, y minus y1, z minus z1 equals 0. And that is the scalar 0. It's a dot product. So a times x minus x1 plus b times y minus y1 plus c times z minus z1 equals 0. And we can use that to represent the equation of a plane in space. Now remember, when we represent planes in a drawing format, we just use a section of them, but this is like a slice through space that extends infinitely in all directions. So it's not just this rectangle, it's that rectangle in every direction, infinitely wide or tall, or however you want to look at it. Okay, so the standard equation of a plane in space, n equals abc, can be represented by the standard form of the equation of a plane, a x minus x1 plus by minus y1 plus c z minus z1 equals 0, and every point on that plane x1, y1, z1, every point on the plane x, y, z will satisfy this equation. The general form of the equation of a plane, when you multiply all this out and collect your constants, is just ax plus by plus cz plus d equals 0. So the d comes from all of the ax1s and by1s and cz1s all multiplied out and added together. Okay, so let's look at an example. It says find an equation of the plane passing through the point 1, 3, negative 7, and normal to n equals j. Now be careful with this n equals j. That throws people at first, but remember that's just 0, 1, 0. So a equals 0, b equals 1, and c equals 0. And we know that we need the k portion of this to be 0 because we're talking about a plane and not a line. Okay, so this is my x1, y1, z1, the 1, 3, negative 7. So putting this in the standard form, I will have a, which is 0, times x minus 1, plus b, which is 1, times y minus 3, plus c, which is 0, times z minus negative 7. And that's all equal to 0. Now, it's pretty obvious that this goes away and this goes away because you have a 0 here. So really we just have y minus 3 equals 0. And this is the general form of the equation of the plane. That's a perfectly valid answer, and if they say general form, that's what they want. There's nothing wrong with writing this as y equals 3. Just, keep in mind this is considered the general form of the equation. All right, now in this case, we're looking at one that is perpendicular, and keep in mind that when you say perpendicular for this, it did say in the definition that it is a normal vector, and normal is another way of saying orthogonal. It's all one of those, depends on which context you're in. So we actually want to use this vector here for our n. So my a here will be 2, my b will be 3, and my c will be negative 1. And I know that's a little backwards from how you normally do things with lines, but remember we're dealing with planes here. And then this is my x1, y1, z1. So we'll have a times x minus x1 plus b times y minus y1 plus c times z minus z1. Okay. And that's technically plus a negative 1 there. So this gives me 2x minus 6 plus 3y minus 6 minus z plus 2 equals 0. And I'm going to take all of my like terms here and combine them together. So I'll get 2x plus 3y minus z minus 10 equals 0. And I'll leave my answer like that. Okay. This example says to find the equation of the plane passing through the points 1, 2, 3, 3, 2, 1, and negative 1, negative 2, 2. So we'll call this P, Q, and R. So notice they didn't give us a normal vector. that's something that we are going to have to find. But it's important to remember that the vector u cross v, so that's the cross product, is always orthogonal to both u and v, or a plane containing both u and v. And I did use the little caret instead of the arrow on top of that vector. They're interchangeable. You'll see me use both, so just don't stress about that, whichever one you're more comfortable with, but you do need to denote somehow that it's a vector and not a scalar. Either one of those is fine. Okay, so that's great, but we need a u and a v. So I have three vectors, p, q, and r. So I'm going to choose to let u be the vector from p to q, and I'm going to let v be the vector from p to r. And this is just kind of an arbitrary choice. You could choose qr. It doesn't really matter as long as they're not the same exact vector or the opposite directions. You want them to be two separate vectors if at all possible. All right, so this will be, see, pq will have 3 minus 1, which is going to be 2. 2 minus 2, which is 0, and 1 minus 3, which is negative 2. And for PR, we'll have negative 1 minus 1, which is negative 2, negative 2 minus 2, which is negative 4, and 2 minus 3, which is negative 1. Okay, so now I am going to find n. So n, and just to keep things consistent, n is going to be u cross v. Now these are 3 by 3s, so we can use the diagonal method here. So I'll have I, j, k. I'll have 2, 0, negative 2, and negative 2, negative 4, negative 1. And then I'm going to copy the first two columns. If you would prefer to use cofactor expansion, you're welcome to do that as well. So when I go through that process and I calculate using the diagonal method, I get negative 8i plus 6j minus 8k. So my a is negative 8, my b is 6, and my c is negative 8 also. So now let's find the equation of our plane. So using the form from earlier, we'll have a, negative 8. Now you can pick any one of the points you want. I'm just going to choose P, which is 1, 2, 3, because that sounds good. So that's my x1, y1, and z1. So we'll have x minus 1, and then we'll have plus 6 times y minus 2 minus 8 times z minus 3. If you had a point that had a bunch of zeros, you might want to choose that one just because it would be easier. Otherwise, I should always go with the first. So we'll have negative 8x plus 8 plus 6y minus 12 minus 8z plus 24 equals 0. And we'll collect all our like terms and get negative 8x plus 6y minus 8z. And then adding all of that together, we will get plus 20 equals 0. And there is absolutely nothing wrong with this answer. If you wanted to submit it, it would be correct. It's just not simplified. So if you wanted to go through and divide by, say, 2 to clear out the common multiple, you could have negative 4x plus 3y minus 4z plus 10 equals 0. You don't have to do that. I just want you to know that it's valid. Let's also take a look at sketching planes in space. If a plane in space intersects one of the coordinate planes, then the line of intersection is called the trace of the given plane in the coordinate system. So to sketch a plane in space, we want to find its points of intersection with the coordinate axes and its traces in the coordinate planes. If an equation of a plane has missing variables, then the plane must be parallel to the axis represented by the missing variables. So for example, ax plus d is missing your y and your z, so it's parallel to the yz plane. by plus d is parallel to the xz plane, and cz plus d equals 0 is parallel to the xy plane because the x and y variables are missing. Okay, so let's take a look at how we do this. We're going to sketch a graph of the plane 4x plus 2y plus 6z equals 12. So what I'm going to do first of all is I'm going to locate the x-intercept, the y-intercept, and this may be a little new, the z-intercept. But it's really straightforward. So to find the x-intercept, and let me get a different color here so you can kind of see what's going on. For the x-intercept, which we'll do in red, we will set y and z equal to 0. So 4x plus 2 times 0 plus 6 times 0 equals 12. So we have 4x equals 12, or x equals 3. So take a look at this if you've never seen a 3D graph before. The positive x-axis on this particular orientation is in this direction. So just look for the letter x and you'll see the positive direction. So I'm going to go out to x equals 3, 1, 2, 3, and put that point there. So for my y-intercept, I'm going to now let x and z be equal to 0. So 4 times 0 plus 2y plus 6 times 0 equals 12. So I get 2y equals 12, or y equals 6. So now I'm going to find the positive y-axis, which is here, and I'm going to count out y equals 6. And for the z-intercept, you could see what happens. We're going to let x and y be equal to 0. So if we do that, all we really have is 6z equals 12, or z equals 2. This direction on this graph is the positive z-axis, so I will go here. So now we're going to sketch the traces. So I'm going to find the xz trace, which is the line that connects the x-intercept and the z-intercept, so that will go here. This is the xz trace. I will have the xy trace, which is the line that connects the x-axis and the y-axis. I'm sorry, the x-intercept and the y-intercept. So this is the xy trace. And I'm going to connect the yz trace, which, you guessed it, connects the y-intercept and the z-intercept. And then we just kind of shade this triangle that forms. It's not a super satisfying sketch, but you can kind of see an idea of the angle at which the plane intersects with the other planes, the xy, the different planes that we're used to, the xy, yz, and xz. Now this is a specific example where the y happens to be missing. So in this case, if you wanted to find the x-intercept, you would let y and z be equal to 0, but there is no y, so we just have x equals 6. So I will put that here. And the z-intercept, where we would have z equals 6. Now since there is no y-intercept, what this is saying is y could be any value possible. So how do you graph this? Well, we're going to graph the only trace we know, which is the xz trace. And then just to demonstrate that this is a plane where y can be anything, meaning this trace can be scooted along this y-axis in any direction, what I like to do in these cases is kind of just draw out a box, or a parallelogram, I guess you would say, and kind of trace out something that is parallel to that line that we just drew, that trace. And I'm just going to kind of make it look a little 3D. It doesn't have to be perfect. And we're just going to shade this rectangle here. Or that's not a rectangle, it looks like a parallelogram. It's technically a rectangle in 3 space. But you can kind of see what we've done here is we've taken a piece of this plane and we're showing that, hey, that can be scooted back and forth. It goes in all directions. And this is sort of the angle that it's forming with the y-axis and the yz plane and the xz plane. Okay, so that is kind of one of the scenarios that you may encounter. You do have to get a little bit creative because it's 3D graphing. It doesn't translate super well to 2D pencil and paper. And this is one of those things that I really believe that advanced 3D modeling and graphing utilities are so much better at than trying to draw this by hand. This isn't an art class, so it's not something that you need to stress out about. But just know that you can find some creative ways to represent these planes on paper if you need to.